Electron diffraction. In 1926, Louis de Broglie suggested that as light had been shown to have some particle properties, perhaps particles might have some wave-like properties. He suggested that the wavelength of these waves would be given by the formula lambda equals h over mv. This is known as the de Broglie wavelength and is sometimes shown as lambda dB. H being Planck's constant, 6.63 times 10 to the minus 34 joule seconds, m the mass, v the velocity, so this is the momentum of the particle. So the de Broglie wavelength is given by Planck's constant over the momentum. Evidence came in 1927 when George Thomson, working in Scotland, and Davison and Germer, working in the USA, independently discovered diffraction, a wave phenomenon, with electrons. Incidentally, George Thomson was the son of J.J. Thomson, who had previously discovered the electron as a particle. Louis de Broglie was to be awarded the Nobel Prize for his theory in 1929, while Thomson and Davison shared the Nobel Prize for their experiment in 1937. This is a simple diagram of their apparatus, with an electron gun firing electrons towards a screen which would glow when hit by electrons. There was a piece of thin metal in Thomson's experiment, graphite in Davison and Germer's experiment. What they saw on the screen was bright rings where the electrons are detected. This is the effect we would expect from waves being diffracted. The electrons were behaving as waves. Now to calculate their de Broglie wavelength. The electrons gain energy by being accelerated through a potential difference or voltage V. The energy gained is given by E, V, where E is the charge on the electron, 1.6 times 10 to the minus 19 coulombs. Electrons actually have a negative charge, but the energy clearly cannot be negative. If the accelerating potential difference is, say, 2000 volts, the electrons will gain a kinetic energy of 3.2 times 10 to the minus 16 joules. The kinetic energy is half mv squared, so rearranging, the speed would be given by 2 times the kinetic energy over the mass of the electron. The mass of the electron being 9.1 times 10 to the minus 31 kilograms. So, the electrons will be travelling at V is equal to 2 times the kinetic energy, 3.2 times 10 to the minus 16 joules, over the mass of the electron, 9.1 times 10 to the minus 31 kilograms. This gives a speed of 2.7 times 10 to the 7 meters per second, roughly 10% the speed of light. Lambda is equal to h over mv, Planck's constant over momentum, which is 6.63 times 10 to the minus 34 joule seconds, Planck's constant, over the mass of the electron times the speed of the electrons. This gives a de Broglie wavelength of 2.7 times 10 to the minus 11 meters, a very small wavelength. This is around about the wavelength we'd expect of X-rays. As the PD was increased, the rings became smaller, as would be expected if the wavelength was getting smaller. This is the same as we see with diffraction of light or with water waves. The electrons were behaving as waves. Electron microscopes use the wave properties of high-energy electrons to see smaller objects. Waves cannot resolve anything smaller than their wavelength, and as electron waves can have smaller wavelengths than visible light, they can provide images of smaller objects.